Welcome back to section 15.4. We're continuing our conversation about percentiles and quartiles. So when we talk about percentiles, sometimes we make the error of thinking that means percent correct. So this is a common source of confusion, that their percentiles what they got correct. So they're very different things. A performance as a percentile tells us how they did in comparison with other students. So if they scored in the 75th percentile, that means that 75% of students who took the test had the same or lower score. The percentile is relative to other students. It does not tell us what percent they did correctly. So for example, it could be that a student got 90% of the test correct, so they scored a 90, but 75% of the students who took the test scored 90% or less. So what does that mean? Let's think about this for a second. So I know that they got a 90% correct, but if I'm comparing it to other students, 75% of students scored a 90% or less. So scored this value or less. So this score is the 75th percentile. And so they may have gotten a 90% correct, but based on how they compare to the rest of the class, that is their percentile. And they can be kind of tricky. So another thing we want to make sure we understand is how to relate quartiles and percentiles. So don't forget that quartiles are just special named percentile. Q1 is the 25th percentile. The median is the 50th percentile. And the third quartile is the 75th. So what is the difference between scoring in the 90th percentile on a test and scoring 90% correct? So if you score a 90th percentile, a percentile is a comparison to others. So that means that I scored, or this student scored better than 90% of peers or other students. 90% correct means they got 90% right on exam. So that is the difference between those two. It can be really tricky to make sense of that vocabulary. What is the purpose of reporting a student's percentile on a state or national standardized test? How is this purpose different from reporting the percent correct? So what's the purpose? Well, this gives relative position, right, to their peers. And it can also give relative position to other states or to the national average to let you know how it's a comparison. And then percent correct will let you know how much you know. This will let you know how you did, but it is not a comparison to others. It's only for your score. So you give this a try and think back to the previous problems that we did when we counted up the dots and divided. So if you're forgetting what I mean, go back to the slides or rewatch the previous part for example 7. That'll help remind you. And then don't forget how the percentiles and quartiles relate as you complete this quartile, and then press play when you're, this problem, and then press play when you're ready to see the solution. There we go. Now we're going to talk about something you may not have learned before, and it's the mean absolute deviation. Now, we saw that when we use a median to summarize data, that we relate it with interquartile range to describe how spread out it is. So now when we talk about the mean, it's more natural to use the mean absolute deviation. So this is the mean of the distances of the data from the mean. And we call it like the MAD or the MAD. So to find the MAD, carry out these steps as illustrated. So we're going to do the steps like this. First, we've got our data set. Here's our data set. Next, we're going to calculate the mean. So we add it up and divide by the number of numbers. Here's our mean. Then we find its distance to the mean. How far is 3 from 6? How far is 4 from 6? How far is 6 from 6? 7 from 6? 10 from 6? Then the MAD is the mean of those differences. So we would add up all the differences, divide by the number of numbers, and this is our mean absolute deviation. So it has a mean of 6 and a MAD of 2. So when data is presented in a dot plot, it's actually nice to compute it as follows. What we do is we would say, okay, the mean is 3. So then instead of the dots, I'm going to write its distance from the mean. So this is 2. The distance from the mean is 1, 1, 1. The distance from 4 to the mean is 1. The distance from 5 to the mean is 2. And then I add them all up and divide to get the the MAD. When we use the mean and the MAD to summarize the data, it tells us what is typical. Mean tells us what is typical, and the MAD tells us the dispersion. The bigger the MAD, the more spread out the data. So here we can see, all right, this is 1.2 and this is 0.2. So dot plot B has a lower mean absolute deviation and less variation. And you can see it if you look at the way it's spread out. These are more spread out and these are closer together. So when we use measures of center and variation, so to make comparisons, this is what we do. So we want to investigate the difference. And that's what we're talking about here. So for example, suppose they want to determine whether giving students grapes and water before taking a test helps them do better. So they randomly assign students to a grapes and water group or a control group. Then they give all the students a 10-point quiz and find the mean are 7 for when they get the grapes and water and 6 for the control group. So on average, the grapes and water group scored 1 point higher. But how much of an effect did it really have? And that's when we can look at variation. So complete this exploration and then press play and we'll discuss it. So let's return back to that exploration. In both scenarios, the difference in the mean was 1 point, but that 1 point makes more of a difference in the first scenario than the second. There is much less overlap in the two distributions in the first scenario than in the second because there is much less variability in the first scenario than the second. So how can we quantify this distinction? Because the MAD is a measure of variation, let's relate the difference in the means to the MAD. So here's the mean, here's the mean, here's the mean, here's the mean. Let's get the MAD. So now we can see in scenario 1, the MAD of each distribution is 0.7. Okay? The MAD is 0.7. So the 1 point difference in the mean is more than 1 MAD. It is about 1.4 MADs. In scenario 2, the mean absolute deviation in each is 1.4. So the 1 point difference is less than 1. It is about 0.7. So viewing the difference in means in terms of the MAD gives us a way to describe how important that 1 point difference is in terms of the scenario. So in scenario 1, the grapes and water had an effect of 1.5 MADs, which is more than an effect of 0.7 MADs. So let's just make sense of that a little bit again. So in scenario 1, the mean difference is 1 point. But how is that in terms of the mean absolute deviation? Well, 1 MAD is equal to 0.7 points. So we can see that the mean difference is more than 1 MAD. Do you see that? It's more than 1 MAD, right? Because that's only 0.7 and this is more. Okay, and then in scenario 2, the mean difference is 1 point and the MAD is 1.5 points. So the mean difference is less than 1 MAD. So we can say that there's more effect, right? The grapes and water had an effect of more mean absolute deviation. So it had more of an effect. So that's another way to kind of compare these here. Let's do an example. Compute the mean and the MAD for each of the dot plots. All right. So I'm going to do that same thing that I can do before. I need to first find the mean, and then once I find the mean, I'm going to calculate the distance. So I'm going to add up all these values and divide by their total value, the total number of numbers here. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So when I add all these up and divide by 10, I get 2.25. So the distance of 1 here is 1.25. This is 0.75, 0.75, 0.75, 0.25, 0.25, 0.25 the other way, 0.25. Over here, I've got 1.25, and then over here, I've got 2.25. So when I add up all those numbers and divide by 10, I get a mean absolute deviation of 0.8. You do that too. Take your time, make sure, subtract, 2.25 minus 1 to see how I'm getting these values here. And then for B, let's get the mean. So I'll add up all those values and divide by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I get a mean of 3. So now that's 1.5 away. That's 0.5, 0.5, 0, 0, 0, 0.5, 0.5, 0.5, and 1. Add all those up, divide by 10, and I get an MAD or a MAD of 0.5. All right, so use the means and the MADs from part A to discuss how the fluoride levels compare. All right, so first of all, I can say that the fluoride in B, the fluoride in B is higher. The average, fluoride B is higher, right? By 0.75. The average is higher. It has higher fluoride. Now that's comparing the means. Let's compare the MADs. What has more variation? Well, this is a greater MAD. So fluoride B, the location, actually it should be location B. Location A has more variation than location B because the MAD is higher. So the difference in means, how confident can we be in distinguishing the levels of fluoride in the water? So the difference in means is 0.75, right? 3 and 2.25. And that's large compared with the difference in the variability. So the difference in the means is 0.75 and the difference in the MADs is 0.3. So that is way more than the MADs, right? So we can be confident that fluoride B we can be confident that there is more fluoride in location B because the mean is higher and the difference in those means is a lot more than 1 MAD. It's almost 3 MADs, right? So we can be pretty confident there. So go ahead and give this a try. Press play when you're ready to see the solution. And we'll continue on when we come back.